This presentation is the Kerry Rowe lecture that I presented about a year and a half ago in Rome. And I'm going to go fairly quickly, so hopefully we can have a little discussion. I'm assuming most people have some foundation in geotechnical engineering. My email is in this first slide, and also my website has the paper, and there's an supplemental material on my website and many other references that I've authored. And the paper from the Rome conference is posted on my website, but a better one actually is there's an update on Geosynthetics International. It was published in 2024 January, but it's never made an issue yet. They're trying to hold all these special papers and make one big special issue. So it's on the website for Geosynthetic International. You can access it there if you want to get that. Okay, so then with no further ado, we'll jump into this discussion of geosynthetic shear strength interfaces and the concept of strain softening. So it's 4 parts. We'll go over some basic concepts very quickly. We'll talk about some interface shear properties that are typical of geosynthetics, then talk about this phenomenon of progressive failure and strain softening, how it relates to geosynthetics, and I'll end up with 5 slides on conclusions and recommendations. So to start, part 1, basic concepts, we will go and review some basic items. I'm just getting my screen set up here. Okay. When you perform stability analyses for any geotechnical situation, this slide summarizes kind of the big picture of the setup. Of course, the geometry is all important. That sets up the basic problem. After geometry, you need to understand the material properties. Most stability analyses are performed with what's called limit equilibrium analyses, and the most important material properties are the shear strengths of the materials, and in a distant second are the unit weights. The unit weights tend to not be that important, but they can be important if there's variations of unit weights. Now, if you use numerical continuum analyses, you may need many other constitutive properties. Now, next to gravity bringing slopes down, the thing that causes slope failures, the second most important one, is pore pressures. Liquid or gas pore pressures are very important to understand and to model in your analyses. There's also dynamic forces for large bodies of soil and waste, seismic analyses, or for thinner veneer constructions and small slopes, equipment loading. And then it's important to understand, along with the geometry, is the sequence of the filling and the timing of how a site is developed. So those are your basic inputs. Then there's the method of analyses. As I mentioned, the most common method used worldwide are limit equilibrium. These approaches have been used for a century, and they're very well understood and calibrated. There's more and more numerical continuum analyses being performed, and we're going to discuss some of those. When you do an analysis, most analyses are done 2-dimensionally, and you have to select the critical cross-section, so that takes experience and judgment. And for limit equilibrium analyses, you have to select the critical surface. Now, there's some algorithms that help you select that critical surface, and with geosynthetics, it's very commonly along part or all of a geosynthetic interface. With continuum analyses, they sort of find the critical surface themselves. That's a different animal. Then finally, what are your acceptability criteria? Most commonly, historically, has been something called FS, or the factor of safety. More and more, we're understanding that everything is statistical and there's probabilities. So PF stands for probability of failure, or it's inverse is called reliability. And what's really powerful is to combine factor of safety with probability, and it gives you a much stronger understanding. And then when you have seismic analyses, you would also have some acceptability criteria related to deformation. How much does the structure move when it's shaken by an earthquake? And then you would say if that's acceptable or not. Okay, so in the world of stability analysis, we have large global analyses where you take the whole landfill or the whole mine body and you look at it, and it's a very large body like this. You can have hundreds of feet or meters. I'm going to be mixing units. Sometimes I'll do English, sometimes I'll do metric. I apologize for that. So you may have these large bodies, and there's a liner system in what we're talking about today at the base of this body, and the critical slippage might be along partly or entirely along the geosynthetic interface. It may go along the whole bottom and then up the backside, or along the bottom and then daylight up through the waste or mining material. Now, we have to recognize that you can also have a global stability failure that is beneath the liner system, and that's very important to check, but it's not the subject of this talk. For what we call cover systems, which are sometimes called a veneer construction, where you have a relatively thin layer being constructed on top of a geosynthetic, the laws of geotechnical physics are the same. The geomechanical laws are the same, but what's different is that the system is much, much more sensitive to pore pressures. Very small changes in gas pressures from below or water pressures from above affect it. And so it becomes a different kind of a system to think about. Even though the geotechnical laws are the same, it's much more sensitive. All right, so the basic historical evaluation dealt with factor of safety, and it really is a simple ratio of what's the strength of your system divided by the forces acting on the system. So if your strength is much greater than the forces, you have a factor of safety greater than 1. How much greater than 1 do you need? Historically, for stability analyses, this number of 1.5, the factor of safety of 1.5 is embedded, and it's a very strong tradition in geotechnical engineering. And it's just because of historically that has worked. Is that applicable to geosynthetic systems? That's what we're talking about. So here's a couple of definitions just to be clear. With geosynthetics, it applies to anything, but relative to geosynthetic interfaces, we can define the peak shear strength, the maximum resistance that an interface has to shearing under a given normal stress. Then there's the residual shear strength. If you shear this material for, let's say, 200 millimeters, quite a long distance, you get to what's called a residual shear strength. And that's when you keep shearing and the shear strength does not change. And both of these shear strengths that we would measure are generally proportional to the normal effective stress. Effective meaning you would remove any effects of pore pressure, and what's the effective stress felt at the interface under consideration, and that's going to be affecting the level of the shear strength that's experienced. Now, with geosynthetics, we have we're going to talk about strain softening. And so we define something that's in between the peak and residual shear strength, and we'll talk about this more. And we call it the large displacement shear strength. And typically we define that at 3 inches or 75 millimeters of displacement. Why? Simply because that's what most shear boxes are capable of measuring, 3 inches. And it's not common that you can get a shear box that does more than 75 millimeters or 3 inches. Okay, that's the introduction. Now we're going to talk about the properties of geosynthetic um, shear, the shear properties of geosynthetics. When we measure the interface shear strength of many geosynthetic interfaces, far and above, the most common method is the direct shear test. There's other types of shear tests that are performed in geotechnical engineering. Triaxial testing is generally not applicable to geosynthetic interfaces, although it's very common with soils. Um, there's one professor that typically performs torsional ring shear tests very commonly, Dr. Tim Stark, and you'll find papers on him, but he's about the only person who does it. Then there's a tilt table for low normal loads that is sometimes used. There's actually a standard in Europe. There's actually no standard in the United States for it, but it is used. But let's say the direct shear test is what's used most commonly. So here's a diagram of a direct shear test. You have an upper box and a lower box, and the area of a large direct shear test is 1 square foot, 300 millimeters by 300 millimeters. That's the top box, and that's the large scale direct shear device. The lower box is generally larger, not always, but I would say most commonly, the lower box is larger. So as you shear, you can get that 3 inches of displacement on the lower box without changing the area. You apply a normal load from the top, and then you shear the two boxes. You measure the shear forces, and the interface is whatever you construct in the top box and the lower box, and where those two come together, you have the interface that you've built into the box. Here's an actual device shown after a test was performed. You can see the lower box had been filled with water. You can see the reflection of the water line to get an idea of what horizontal was. The top half of the box has been hinged and is flipped up. So you can see it's sort of standing vertically. That has a textured geomembrane mounted on the top box. The lower box was underwater. It had a GCL in it. The GCL is still there. The test was conducted at 10,000 pounds per square foot, which I think would be about 500 kPa. You can see bentonite has been squished out the sides of the GCL, and some has come up through the geotextile. And this is a picture after the test has been performed. Okay, so now here's a result, or here are schematics of results. And this points to what we're really talking about. On the left is a typical shear displacement curve for a non-strain softening material, which would occur for medium sands and normally consolidated clays, and some geosynthetics. The curve here is actually from a geosynthetic, which was from a sand, or no, this one is a sand, I'm sorry. But there are some geosynthetics that do show this kind of behavior, whereas as the normal stress is applied, the shear strength increases to a peak strength, and as you keep shearing and keep causing displacement, the peak shear strength stays the same. On the right is an example of what's called strain softening behavior. And this happens with many, many geosynthetic interfaces, especially the most common ones. And it's also characteristic of dense sands and over-consolidated clays. It shows that if you have a given normal stress, as you induce shearing displacement, usually around 10 millimeters of displacement, you hit your peak strength. So the strength is increasing, and finally it hits a peak strength, and then it starts falling off. It starts decreasing, and it's in this post-peak shear strength zone, and with enough displacement, eventually it asymptotically approaches a residual shear strength value. And then as shown on here, in geosynthetic engineering, we often call out a large displacement value, and we simply define it to occur typically at 75 millimeters of displacement. You can pick any number you want. Some people have used 50 millimeters, for example, for their definition of large displacement. But by and large, the industry has settled on 75 millimeters most commonly. So this next slide shows some actual shear strength test data for a very common interface that's used in waste containment facilities and mines for a textured geomembrane against, in this case, it's a geocomposite that where the shearing occurs against a non-woven needle punch geotextile that's heat bonded to a geonet. And there's 4 curves here where each test was conducted at a different normal stress, representing the normal stress range that was anticipated for that project. In this case, from 96 kPa up to 766 kPa. And you see each curve is showing this characteristic strain softening behavior with a distinct peak, and at a relative displacement around 12 millimeters, somewhere in that zone, it hits its peak. And then it falls off. And it's heading towards a residual strength. And here you can see the test went out to 75 millimeters because that was the length of the box. To get to true residual, you'd probably have to go to about 200 millimeters. So now from this data, you develop what are called the shear strength envelopes. You plot the normal stress versus the shear strength. And that's what we're going to show on this next slide. From those curves you just saw, these envelopes were plotted where you plot the peak strength that was measured at each normal stress, and then the large displacement strength at 75 millimeters as a function of each normal stress. When you fit a straight line through those sets of data, you end up with what are called Mohr-Coulomb shear strength envelopes. In actuality, nature says that the shear strength curves are typically, with soils and geosynthetics, typically a curve that's better approximated by a hyperbola, and you can write equations for a hyperbola. And there's many computer programs that can take that into account in different ways. But historically, we've used linear interpretations, and the slope of a line where you draw this is called the friction angle. And the intercept on the y-axis is often called the cohesion or adhesion. And so here we can see the upper line has a peak strength of 23 degrees friction and an adhesion of 34 kPa. The lower line has a friction angle of 8 degrees and a y-intercept or an adhesion of 33 kPa. Well, great. We have 2 shear strength curves from the same shear stress data. Which curve do you use for design? That's the question of this. That's the topic of this presentation. So, if limit equilibrium analyses are used, again, which shear strength curve do you pick? The peak, the large displacement, somewhere in between, or do you actually go out to residual? And which factor of safety is acceptable for that level? Well, here's just a few considerations. A lot of historic analyses would use peak strength and use a factor of safety of 1.5. That is not allowed in California for bottom liners of landfills because everybody knows there's a lot of earthquakes in California. There's actually a lot of earthquakes in many other areas, but except for the state of Ohio, there's no other places that have this requirement in the United States. California requires a factor of safety of greater than 1.5 for landfills for large displacement. So you must choose the large displacement shear strength in California. Like I say, except for the other state of Ohio, there's no other state, to my knowledge, in the United States that currently has that kind of requirement. And as I say, what about residual strength? I mean, what's so magical about 75 millimeters of displacement? It could go much more in an earthquake, so maybe you want to use residual. Many designers, including myself, recommend that you check the factor of safety with residual shear strength and maybe just require that the factor of safety be greater than something like 1 or 1.1. So now I want to point something out that in the industry, in the literature, often and in vernacular discussions at conferences, people get sloppy and they talk about the residual strength when they're actually meaning large displacement because it's easier and quicker to say. Very few people actually measure the residual strength. So they assume residual and large displacement are synonyms. That is not correct. They are different, as I explained previously. Okay, let's go into part 3 and talk about progressive failure. All right, now, as we said, you can measure these different shear strengths. Here's from a slide from Tim Stark. From the same set of shear data, you can get the peak strength curve, here 32 degrees for this interface. You could get the large displacement curve, which he used 50 millimeters. And he actually measured the residual strength because he used his ring shear device and he got 13 degrees. And there's an infinite number of curves in between the peak and residual you could choose as well. What do you choose for your design? That's the question. Now, related to progressive failure, this concept of progressive failure started in geotechnical engineering. The awareness of it was really defined in 1964 by Sir Alex Skempton because they were studying over-consolidated, stiff, fissured clays where these failures would happen many years later after they would cut a slope next to a railroad, especially in England, and there was these failures that occurred. And he came up with this paragraph, and I'm going to read this out loud where I substitute the words geosynthetic interface in place of where he used the word clay. So if for any reason a geosynthetic interface is forced to pass the peak at some particular point, the strength at that point will decrease. This action will throw additional stress onto the geosynthetic interface at some other point, causing the peak to be passed at that point also. In this way, progressive failure can be initiated. Once a progressive failure has started, the average strength of the geosynthetic interface will decrease inexorably towards the limiting residual value. Wow. So this is where the concept of progressive failure was really defined and it took a long time for the industry to really embrace it. And we're still struggling with it, quite frankly. How do you deal with it? Does this mean we have to use residual strength everywhere? This is the question. So as I mentioned, limit equilibrium analyses are most commonly used, and there's many variations of limit equilibrium analyses, which were first defined 100 years ago using the Swedish method, and now it's more commonly, there's Bishop's method, which is typically used for circular surfaces. Spencer's method is probably maybe the most common method used because it's very robust and it's uh, easily, or it's commonly programmed into a lot of the software programs. Morgenstern and Price is a little bit more sophisticated, but it's also common because we have such good software these days. The Yanbu method is particularly useful for doing a lot of quick searches. I typically do a lot of searches using the Yanbu method, and then I do my final analysis using Spencer's method. There's other methods too, but what do all of these limit equilibrium analyses have in common? They all assume that the soil or waste mass acts as a rigid body. They all do that. And this is totally fictitious. It's a limitation. And it's unrealistic and unconservative for strain when if there is a strain softening interface. The only way it can be conservative is if you use residual strength. That is a fact. So the point is, even if you base your design on peak strength or even a post strength that's higher than a post peak strength that is higher than residual, and you use, say, a commonly used factor of safety of 1.5 based on a limit equilibrium analysis, your structure could still fail because of this mechanism of progressive failure if you have a strain softening interface. And the reason is there's a non-uniform mobilization of shear stresses that occurs that's impossible to model with limit equilibrium analyses. In addition to this non-uniform mobilization of shear stresses, there's other localized degradation mechanisms of shear strength that can lead to displacements that degrade the shear strength. And strain softening is the degradation that's the result of that degradation. All right, let's look at a couple historical examples. This all started in the waste containment industry in 1988 with the Kettleman Hills landfill failure, the largest hazard permitted. There might be larger unpermitted ones, but the largest permitted hazardous waste facility in the world at the time, and maybe still, 490,000 cubic meters of waste slid on geosynthetic interfaces and brought home the issue of progressive failure. This is a aerial view on the left of the actual post after the slide, and on the right is a diagram. And here, this issue of progressive failure was first addressed with a numerical analysis in 1994 by a fellow from Golder named Byrne. And it's kind of a complicated diagram, but he was showing how the shear strength mobilization was not a uniform thing that could be predicted by limit equilibrium analyses. So he used finite element analyses to show this diagram. And then kind of the next major publication on this kind of issue was presented by our friend Krishna Reddy in 1996 with some of his graduate students. And he did also a different finite element analysis program, but again, it was numerical continuum analyses. And it's a fantastic paper with lots of correlations of texturing and displacement, smooth versus textured, and variations of slopes. But the cross-section that he used was basically the Kettleman Hills cross-section. Not exactly, but very close to the classical Kettleman Hills landfill. And the key point here is that the mobilized shear stress, which is the squares, was not related to the normal load. It did not. It was a non-uniform mobilization of shear stresses where shear stresses were mobilized primarily along the outer toe and the backside slope. Okay, so that is key because that's where you might start your progressive failures. My favorite one, though, for Kettleman Hill history was in 2001. There were a pair of papers by Phils, Esterhuizen, and Duncan, and they analyzed yet another finite element analysis program, or it might have been finite difference, I'm not sure, but numerical continuum analyses, and they did it layer by layer, modeling Kettleman Hills landfill failure. And they actually, because the liner system was like more than 2 meters thick with all these different interfaces, they showed that there was one interface with a smooth geomembrane against a geonet and another critical interface that had a clay against a smooth geomembrane. And they showed when it got finally at the critical height, they were into residual strength at the toe and the back slope. That's where the shear stress is first mobilized. On the geosynthetic interfaces, they still had peak strength left in those zones on the clay interface, but in the middle of the landfill, where you had higher normal stresses, it was the clay that had progressive failure, and it was at its residual strength, and the geosynthetic interface was still at peak strength. So at just before failure, there was only one tiny little zone in the middle of the landfill that still had peak strength available in all the layers. But by that time, the straw that broke the camel's back was placed in the landfill and it failed. It's a fantastic article. Now, there's not much literature that does this degree of description for the average engineer to review. I highly encourage any practitioners who are doing slope stability analyses to study these references. And there's only a couple more since then that really show this, and they're a little bit obscure. But it gives you a feeling, if you're not running numerical analyses yourself, it gives you a feeling how shear stresses are being mobilized at the bottoms of these structures in a non-uniform way because the soil and the waste are not rigid bodies. They're deformable masses, and that causes the mobilization to occur. Let's look at another case history. This is interesting. This is the Rumpke landfill failure that occurred in 1996. 1.1 million cubic meters failed. There were fires and gas, and it was just a big failure that happened relatively quickly. It went like 120 meters. It slid, which is a sign of a progressive failure. These often happen in a relatively short period of time, and they go large distances. It had a 60-meter high backscarp up through the waist, and the failure at the bottom was along a layer, I think it was like a 1.5 meter thick layer of native brown clay soil. The amazing thing, when you look at the shear strength characteristic of that native brown clay layer soil, it's almost identical to a common geosynthetic interface of a textured geomembrane against a geocomposite. The upper two curves here, the dotted curve is the peak shear strength of a textured geomembrane to a nonwoven geotextile on a geocomposite. The solid line is that native brown Rumpke clay. The dashed line here is the large displacement shear strength of a textured geomembrane against a geocomposite. The dashed dot is the residual shear strength of the Rumpke native brown clay. It could have been a geosynthetic when Rumpke failed. It was a classical failure that could have been a geosynthetic interface. The lower graph is simply one of I only had the data for 50 kPa, which is a low normal load for both interfaces, and it shows that they both had peaks close to each other, and they had large displacement shear strengths that were getting close to each other. So that's an interesting case history. Here's a confidential case history that happened in the Midwest, not far from Krishna, where 300,000 cubic meters of waste slid, and the failure was between a geomembrane and compacted clay, and it has all the signs and characteristics of a progressive failure. Another confidential history that occurred in the last dozen years, a completed landfill that was filled, and then some years later, it failed along the bottom liner system, the slippage between a textured HDPE geomembrane and a nonwoven geotextile. 620,000 cubic meters of waste slid, something like 22 meters, went out into the road. The entire failure was almost like 95% of the failure was along this geosynthetic interface. And it had all the signs, again, of a classic progressive failure. And then in the world of veneer cover systems, we've had hundreds of veneer cover system failures. Why? Again, because earlier I mentioned cover systems are so sensitive to pore pressures, little tiny changes in pore pressures. And these failures occurred along geosynthetic interfaces. Like I say, there's hundreds of them. And they're all characteristic of progressive failures. So in my uh, in my lecture that I prepared for Carrie Rowe, I identified 15 mechanisms. This is, I think, is the largest list available of mechanisms that can lead to progressive failure that uh, along strain softening interfaces, which most geosynthetics have strain softening interfaces. And now, this list, you could argue that a lot of these mechanisms might be related, they might be overlapping, but it's useful to identify specific mechanisms because then as an engineer, you can try to address these specific mechanisms. And that's the value of identifying mechanisms. You'll have to read the paper to go through them in detail. I'll just mention that mechanism number 2, waste settlement, is commonly historically has been the most commonly cited mechanism, the down drag caused by waste settlement, re reducing the shear strength. I'm going to discuss at this presentation today a little bit about construction-induced degradation and then material variability, 14 and 15, material variability in manufacturing and installation. Just a quick example of down drag. This was an interesting thesis in 2007 by the Loughborough University group, Neil Dixon in charge there. Since he's now retired, showing how down drag created tension that tore the geomembrane at the crest. Another publication by Dixon's long-term favorite student, Jones, David Jones. And here's one of the few, again, continuum analyses, finite element analyses, showing how settlement of the waste with a textured geomembrane against a non-woven needle punch geotextile, the settlement caused 3.2 meters of displacement at the crest. Did not cause a slope failure in this model, but that surely would have caused something to rip and tear at the crest. There's been actually quite a few papers. Here's 1, 2, 3 papers in the last 10 years that have looked at this down drag issue and how from the crest and the localized crests of benches, down drag causes this tensile strain to occur in geosynthetics and may cause them to rip. Now, the focus is on the strain in the geosynthetics in these studies and why you should maybe have a slip layer here so you don't rip your geomembrane. For our discussion today, what we're interested in is the fact that there is down drag, there is displacement, and the shear strength will be reduced, and you have to take that reduced shear strength into account for the global stability. So it's a different issue, strain versus shear strength, but they're both related to this mechanism of down drag. And this was introducing a weak interface with a slip layer was first introduced 30 years ago by Snow et al. In this publication where they put a slip layer. Now, if you put a slip layer there, you're introducing a weak layer. And so you have to deal with that in your slope stability analyses and have proper sequencing in your landfilling or your mining. Okay, enough on down drag. Just want to mention a little bit about construction damage. When you spread gravel on a slope or soil on a slope on top of geosynthetic, you create localized stresses underneath the tracks of the dozer or the pile of material that the dozer is pushing. There's huge shear stresses right underneath that pile. Now, historically, I've reviewed dozens of engineering calculations for regulatory agencies or doing peer review for engineers. And the only analysis I ever see when people look at the construction of veneer layers on slopes is they look at the entire slope, they model the equipment as a point load, and they look at the shear forces and the normal forces, but they look at the stability of the entire slope. That's common, but that's not what I'm talking about. I'm talking about what happens right underneath the dozer, the shear forces right underneath the tracks, the shear forces right underneath the pile. This was first addressed in 1999 by two independent papers, one by a guy named Kirkies that was published in the Boston Geosynthetics Conference, Geo 99, and then also by Richard and Peruvicott and Richardson in the Geosynthetics magazine in 1999. But nobody ever uses those for their analyses. I'm not sure why. Here's what happens. If you uncover an area where there has been aggressive pushing, you find that there's bunching and wrinkling of the geosynthetic caused during construction. And that is weakening, that's reducing the shear strength. That is causing locations where progressive failure might occur. Here's where progressive failure resulted in a failure. During pushing, it was loosening up that interface until finally it slid. I've looked at this. I've done testing. I show if you pre-shear an interface at 24 kPa, which is the load of say the dozer working, you pre-shear it, and then later on, if that experiences a higher normal load of, say, 192 kPa, you reduce the peak shear strength by 13%. Or again, if you pre-shear it during construction, the long-term low normal stress shear strength can be reduced by 42%. You reduce the peak strength by 42%. So construction-induced pre-shearing degrades your peak shear strength. To make this simple and easy to evaluate for engineers, myself and JP Giroud wrote a couple papers in the last couple of years. They're available on my website showing the different cases of what happens below the dozer tracks or what happens below the pile being pushed, pushing upslope, pushing downslope, what happens with deceleration. You can generate curves like this, and basically you're trying to figure out how big of a pile of soil can you push with a dozer when you're going upslope or going downslope, or how quick can the dozer stop? And it's really specific to the slope inclination, the exact weight and dimensions and width of the tracks, length of the tracks of the dozer, the thickness of the layer being spread is very important. The internal friction angle of the soil being spread is very critical. That's what's on this x-axis. What's the internal friction angle? And then, of course, the interface friction angle. You'll get different curves depending on what the interface friction angle is, the peak strength. And then this is very easily encoded on a simple spreadsheet. And I hope designers can start looking at that using these spreadsheets. Okay, another mechanism that will cause progressive failure due to this strain softening are variabilities in some of our materials. We have variability in the texturing of geomembranes. You can see different asperity heights. You can see tiger stripping, okay? During manufacturing of cast textured geomembranes, you get filling of the additives fill up the little dimples in the cast, the engraved rollers, and then the height of the texturing goes down. So basically, you get a lot of variation of texturing. Needle punching of GCLs, you can get different, it can degrade with needle punching as the production goes, or it can vary from one side of the roll to the other. I'm going to give an example of the variation of heat bonding of the geotextile to a geonet for geocomposite. This probably, at least in North America, has the highest standard deviation of any material property for geosynthetics. In 2017, I experienced a project where we noticed there appeared to be uh, delamination in loose areas between a bonded geotextile and a geonet that had already passed conformance testing. So the specification was 1 pound per inch or 175 Newton per meter. Um, that was the specification for the peel strength. And in the ASTM method, they cut 5 random samples and you average them and it passed. But if we took continuous samples across the whole width of the roll in a checkerboard pattern, and I'm plotting along the width of the roll, I'm plotting the results from each sample, and you can see this huge variation in peel strength across the roll. And it was shocking to find out that 1/3 of the results were below the specification. The average was well above the specification, the average of all of them, but 1/3 of them were below, and 18% of them were less than 1/4 of the specification. They were so low that just the fact of rolling the material up and unrolling it might cause it to delaminate. So I'm going to assume that you could have 16.2% of your net installed area might be delaminated, even though you have an average that is well in excess of the specification. Okay, now we're going to combine that with variabilities of shear strength caused by seaming, standard industry practice of seaming. I've never seen this taken into account by other engineers doing stability analyses. For example, when you overlap GCLs 150 millimeters or 6 inches, some people overlap them 300 millimeters. About 2% of your area is going to have hydrated bentonite on that distance. 2% of the area is going to have a friction that's probably on the order of 5 degrees friction angle. These days, when you order textured geomembrane, it almost all comes out with smooth edges, where the smooth edges are typically 0.15 millimeters wide. You overlap in 0.1 meters. And so you end up with a net 0.2 meter smooth zone against some sort of a geotextile. So 3% of the total area ends up with a friction angle that's somewhere around 10 degrees friction, say a little bit less than 10 degrees. Again, I'm going to show an example. The problem child is really these geocomposites that often come with an unbonded edge distance of 0.3 meters. They're overlapped 0.1 meter. It results in a 0.5 meter of unbonded edge every 4.32 meters. Basically, 11.6% of the area ends up with a low friction angle where there's an unbonded geotextile on a geocomposite. Now, I want to make a quick note that the geocomposite, let's say it's installed on a 3-to-1 slope, 18.4 degree slope. The low friction angle is parallel to the ribs, and it depends on the product, but for this particular product, the angle of the ribs on the GeoNet were at 25 degrees from the roll direction. So if you put it down the 3-to-1 slope, you'd be 25 degree, and the inclination on an 18.4 degree slope skewed 25 degrees is a 16.7 degrees. Okay, so just keep that in mind as we move forward with this discussion. So let's consider the implications of some of the stuff I've said for a typical, what I call Eastern United States double composite or double liner system for landfills that's required by the regulations. There's 2 layers of geomembrane, typically textured. There's 2 layers of geocomposite, and there's 1 layer of GCL. This is common Eastern United States design. And then the top is covered with a gravel that's spread by the bulldozer, right? Let's see you put this on a 3-to-1 slope and let's see what might happen. Okay, here's a 3-to-1 slope, 18.4 degrees, just a generic area, right? Okay, first layer goes down and is the secondary geomembrane. And we have seams, 3% of the area has this low friction angle, less than 10 degrees, and we're on an 18.4 degree slope, right? Now we put our first geocomposite, and it has these unbonded seams, 11.6% of its area. And we note that the critical shear strength's at the skew angle, so it's on a 16.7 degree inclination. All right. So now we're up to 14.6% of the area having a low friction angle on a 18.4 degree 3-to-1 slope. We put our GCL, let's assume the GCL stays dry. That's non-conservative, but let's just go right to the primary geomembrane that's installed, and that adds another 3% for its seam area. So now we're up to 17.6% of the area at this skew angle, having a low friction angle. And then we install the primary geocomposite, another 11.6% of the area. Now we have 29.2% of the area having this low friction angle. And this is with standard, this is just counting standard installation seams. No defects, no other problems. Right out of the gates with standard installation, assuming the GCL stays dry, you have 29% of the area at less than 10 degrees friction. I have not seen engineering slope stability analyses in the projects I've reviewed that take that into account. Now, how much additional weak zones could arise from the manufacturing variability we discussed? Well, let's just consider the geocomposite. I'm not even going to go into the variation of needle punching and texturing, just the geocomposite. Each of the two layers of geocomposite could have, as we showed in that one example. Now, this is kind of worst case, but it's a real case that was experienced. Each layer could have 16.2% that would delaminate. It was less than a quarter pound per inch, whatever that comes out to newtons per meter. Very low. So that adds 32.4%. So now you're up to 61.6%, almost 2/3 of the area has this low shear strength on a 3-to-1 slope, right? Now, what happens when the dozer starts pushing the gravel up the slope? Like I say, very few engineers have considered the restrictions that you need to put on that dozer. It's a question mark. It's just going to make that 61% go up to something higher. It's going to cause further delaminations, further weakening. Does this actually happen? Here is where, this is a photo of an exhumation of a landfill failure that occurred. This is the secondary liner geomembrane, textured geomembrane. It's been exhumed after hundreds of thousands of cubic meters of waste have slid, and there was a failure. And what you see is a 3-to-1 slope, and you see the general slide direction down the 3-to-1 slope. You see the striations on the left. And the right, looking down the slope, you see the striations of the slide failure going down the slope. But what else do you see? You see on the slide on the left, you see some of these striations at this angle coming at you. And in this one up here, you see melted geotextile from the heat of the shearing under the weight of the waste. As it was shearing, it melted the geotextile and it smoothed the texturing in the geomembrane. And again, you see this characteristic angle that's characteristic of the geonet strands that were at that 25-degree angle. Even though the mass of the slide, when it really gave way, went in the downslope direction, we see signs that sliding occurred at this direction too. So you can see evidence of a progressive failure mechanism. There's physical evidence that this occurred. Something happened in this direction, but overall it went in the 3-to-1 direction. So in conclusion, for this typical eastern region, you could say that 29 to 60% of the area, maybe somewhere between these values, would have a shear strength less than 10 degrees friction at the end of construction. And this is where you have textured geomembrane, and the common practice is to do a shear test and assume that the shear strength values you got from your shear test can be used in design. Now, this doesn't even account, once you start putting waste on there, you might get down drag from waste settlement. You have strain incompatibility issues between the waste and the liner system as the shear strengths mobilize. You might have dynamic forces, you might have pore pressures, you have aging, and you have other mechanisms that can lead to progressive failure. These numbers above don't even consider that. Okay, are there mitigation measures we can have to counteract all this stuff? In my paper, I list 12 potential mitigation measures. A lot of them are related to geometry. Um, there's some that we can attempt to preserve peak shear strength. We can try to mitigate pore pressures, and we can do long-term monitoring and adaptive management if you have a good response program. Let's look at a couple interesting ones. One is this idea of modifications to the subgrade. Here's a large heap leach pad where they put in giant speed bumps as part of the bottom liner system, and that greatly improved the slope stability. There's a great paper by Breitenbach and Athanasopoulos in 2013 looking at how you can put speed bumps along the bottom. You can put speed bumps or benches along the slope, and you can greatly improve the slope stability. And you can use a slip surface on the geomembrane because you're improving it with these geometric interruptions. Breitenbach, the same author in 2004, also suggested that dimpling occurs depending on the nature of your bedding soil and your overliner, your underliner, that it's actually not a smooth, straight surface. So the direct shear test is often inherently conservative by having a smooth surface. But if you put in actual materials and you let them sit for a long time, you get this dimpling, and that actually adds to the shear strength. You can do things with greater and greater degrees of texturing so that both the peak and the residual are higher strength, or the peak, in this case, it's the large displacement, are higher than a lower degree of texturing. So there are some things you can do. What you also want to make sure is if you have GCLs, you want to make sure that the internal shear strength of the GCL is never the one that fails, because if that one fails, your large displacement, or actually your residual shear strength of hydrated bentonite, is going to be very low. So when using GCLs, you should specify a very high pill strength. I almost never have a project where I specify less than 12 pounds per inch, according to the more recent standard for peel strength. You'll have to multiply that by 175, and then you'll get newtons per meter. And you can even specify higher than that, although you'll end up having to pay for that. But 12 pounds per inch is, the manufacturers are ready to put that out. Now, if you don't want it to fail below the geomembrane, you want the geomembrane to stay intact. If there is movement, you may have to reduce the asperity height on top of the geomembrane. Now, that's going to create a slip plane on top of the geomembrane. You're going to put lower shear strength, and you have to take that into account in your analyses. And then this method of geometric interruptions that we just discussed is also very powerful. Okay, that brings us to the last part, our conclusions and recommendations. I guess we're running a little long on time. Uh, Limit equilibrium analyses are the most common. They're non-conservative. Strain softening is endemic. Numeric continuing modeling can predict a lot of this stuff, but they're not common and they're not every day. They take a lot of training, time, and they're costly. Slope stabilities need to be done by trained professionals, geotechnicians. Critical geosynthetics are not just commodities, they're highly engineered projects. There should be project-specific testing to determine peak and large displacement shear strengths. Even when you're using large displacement strengths and with peak, you should modify the strengths downward due to the mechanisms described in my paper. Remember, risk is probability of failure times the consequences. I could give a whole presentation on that alone. We didn't have time today. Adaptive management, I didn't talk about it, but it's excellent to do post-construction monitoring and have response action plans that can help reduce your risk. Seismic deformation needs to assume residual strengths, even if you think you can design statically with static peak strengths. You should always use residual for seismic analyses. Attempt to position the critical surface above the geomembrane. For veneer systems, it's common to use peak strengths for veneer systems, but the peak strength should be modified downward to account for the mechanisms of installation and manufacturing variabilities and construction issues. Pay special attention to pore pressures, very important. For bottom liners, anything steeper than 3 to 1 has a high probability of experiencing some sort of displacements that will lead to strain softening. I like the Stark and Choi recommendations to you can assign residual strengths to side slopes, and you can use a modified peak strength on flat areas and have a factor of safety greater than 1.5. Part 1, and then part 2, assign residual strengths everywhere and just check that the factor of safety is greater than 1. So you do both of these, not just one. Or consider having a higher factor of safety when there's more uncertainty. And prepare an operational plan. Make sure you look at the fill sequencing, very important. Consider other mitigation measures like toe buttressing. Be conservative with your assumptions on pore pressures. Don't ignore them. Recommendations for the future, I think we need to do more modeling. Skempton mentioned this in 1964. What's the effect of stress concentrations? Meaning these unbonded areas where you have installation seaming. On a repetitive? Those are like stress concentrations. Those haven't really been modeled. And long-term aging and durability is the holy grail of geosynthetics. And how is shear strength in that area? Well, I hope I didn't run over time very much. Thank you, and I can open it up for any quick questions.
Yeah, thank you. Thank you so much, Richard. That was fantastic presentation. I think